Math 1343, Week 8, Video 1, the Chi-Squared Distribution. The rest of the videos in this series will be the standard me at a dry erase board introducing and teaching a new topic. But for this first video, I wanted to use a Zoom session recording, so that I may share a document, or rather show you where to access a document in Canvas. It'll be a new distribution table called, appropriately enough, the Chi-Squared Distribution. Now, before we get to that distribution, I want to compare what it looks like compared to what we've seen previously. So far, we've seen two types of distributions. The first was the Z distribution. And the Z distribution, whose formal name is the standard normal distribution, is a normal distribution, also known as a bell curve, whose mean is 0 and whose standard deviation is 1. And so whenever we draw the Z curve, if you will, we always put a 0 in the middle. And we've also seen the T distribution. The T distribution is kind of like the Z distribution in the sense that it is a bell curve and it has a mean of 0, but the standard deviation depends upon the degrees of freedom. And so depending upon the degrees of freedom, we may get a curve like you see here, or we may get something that is a little bit wider and flatter, like that, if it has a larger standard deviation. Or we may get something that's a lot skinnier and taller if it has a smaller standard deviation. So the T distribution actually has multiple shapes whose shape and standard deviation depends upon the degrees of freedom. And the formula for degrees of freedom changed from scenario to scenario. In one type of problem, we had degrees of freedom was equal to the sample size minus 1. But in another type of problem, we had degrees of freedom was equal to the minimum of the first sample size minus 1 and the second sample size minus 1. The formula for degrees of freedom when using the T distribution is really context specific, meaning what context are we doing and what is the formula for the degrees of freedom. So what's the chi-squared distribution? Well, the chi-squared distribution, first off, the variable is the Greek letter chi, which looks like an X, but I try to give it a little bit more curvature on the top with a square on it. So this is pronounced chi-squared. 2 words. Now, the reason it's squared is a little bit beyond the scope of this course, but it is the result of squaring something. And since we're only dealing with real numbers, when you square a real number, it will never come out negative. So what that means is that the chi-squared distribution is always non-negative. Now you might be thinking, why didn't I just say positive? Because honestly, positive and non-negative are not synonymous. They're almost the same. The only difference between positive and non-negative is that non-negative means positive or 0, whereas positive means greater than 0. So non-negative is a little bit more broad a description than positive, because it does include the possibility of being equal to 0. So since our chi-squared is always non-negative, we really can't have a picture like this one, like these two, because to the left of 0 on both of these are some negative numbers, and we're not going to have any of those. So what does the chi-squared distribution curve look like? Well, it starts with what looks like an x and a y-axis if you were graphing. So if you can imagine these axes going left and right, it's kind of something like that, but we're only focusing on what would be called quadrant 1 if we were graphing. And the shape of the chi-squared curve actually depends on the degrees of freedom. Let's see. So for low degrees of freedom, our curve kind of looks just like a quarter pipe. It starts up here somewhere and it just kind of does this. So it kind of looks like the right half of the bell curve. But for higher degrees of freedom, it does start resembling a bell curve. And what essentially happens as you raise the degrees of freedom is that this peak, which starts out at 0, gradually moves to the right. And for really high degrees of freedom, we start getting something that looks more like a bell curve. You would get something that looks like this. But it's not really a bell curve because a bell curve extends indefinitely in both directions and also has a symmetry. Chi-squared distribution will rarely have a symmetry. When I sketch a chi-squared distribution, and by the way, I should label this axis chi-squared. And if I'm going to do that, then I should probably go back to the first two pictures and label this axis the z-axis and the t-axis. But whenever I draw a chi-squared distribution curve, in general, I'll usually draw it like the second one here. I'll usually draw it like this, even if the degrees of freedom are low, because we don't really need to be super nitpicky about nailing the exact shape of the chi-squared distribution curve. Again, for low degrees of freedom, it kind of looks like a quarter pipe, for those of you who are familiar with what a quarter pipe is. But the higher the degrees of freedom, the peak of this curve just starts moving further and further to the right. So I will always be drawing my chi-squared curves like the one that's currently inside of a red box. All right, so now that you know what the shape of a chi-squared distribution curve looks like, what does the table look like and how are we going to use it? I'm going to draw this curve a little bit more like I would normally draw it. Well, the chi-squared distribution, well, actually, let's just pull up the table. Let's go to our canvas shell, which is, that is right here. Go to Canvas, and I went ahead and created the week 8 module. And there are two things in it currently, the chi-squared distribution PDF and the week 8 learning outcomes. If we go to the chi-squared distribution PDF, download it and open it in its own tab. You'll notice that it kind of looks like the t-distribution in the sense that there are degrees of freedom on the left, over here, and that there's a right tail area on the top. But if you look at the right tail areas, you'll realize that they're not the same as the one in the t-distribution. In the t-distribution, going from left to right, the right tail areas are 10%, 5%, 2.5%, 1%, 0.5%, and 0.1%. But if you'll notice here in the chi-squared distribution, there's two very distinct groups of right tail areas. We have some small right tail areas. Oops, didn't mean to highlight all of those. 10%, 5%, 2.5%, 1%, and 0.5%. But over here, we have much larger right tail areas, 99.5%, 99%, 97.5%, 95%, and 90%. Each area on the left, like this 90%, has a corresponding area on the right, like this 10%, whose sum is 100%. So here's 95%, and then the remaining 5%, 97.5%, the remaining 2.5%, and so on and so forth. The reason we do this is we can't do left tails and right tails like we did on Z distributions. If we go back to the picture of the Z and T distribution for a second, remember that each of these charts has very specific ways to use them to look up certain areas and certain things. The Z distribution assumes left tail areas, and the T distribution assumes right tail areas. So if we were looking up the area that the chart didn't accommodate, we would have to use symmetry. So for example, if we looked up, oops, didn't mean to erase that. If we looked up a left tail and it was a certain percent, we'll call it alpha percent for significance level. And we got Z equals negative 1.96. But over here on the right side, we had the same area in the right tail, and we wanted to know this Z on the right, we would just use symmetry and say 1.96. And we would do the same thing in the T distribution. Well, why can't we do that in the chi-squared? The answer is simple. There is no symmetry, and there are no negatives. So if I were to have a tail over here that was an area of 5% on the right, from the left we cut off a quote-unquote tail, and I'm kind of reluctant to call it a tail because it doesn't go forever to the left. But if we had the left tail, if you will, shaded off at 5%, then these chi-squared values could not possibly be opposites because they're both positive. So how would we find them? Well, let's assume the degrees of freedom are 10. So just for the sake of having a degrees of freedom to look up in the table. If we go back to the chi-squared distribution table and look in the 10th row for the 10 degrees of freedom, we have all these chi-squared values going from the left to the right. The key thing about using this table is understanding that it wants the area in the right tail. And I think I'm going to go rewrite this table so it doesn't say area in the right tail, but rather area to the right of a chi-squared value. If we were to use this table to find the chi-squared value on the right, where the right tail is actually 5% with 10 degrees of freedom, then we would literally just go to the 10th row and look under 5%. Let's do that. I can get back over there. All right, 5% in the right tail is right here. Look at it carefully. 10th row is down here. And so that 18.307 is our chi-squared value. I think I said 18.307. We'll go back and check in just a second. 18.307. Yes. But what about the left tail? The left tail has 5% in it, but our chi-squared value, our chi-squared table, needs to know what's to the right. So if the left was 5%, then the right would be 100% minus 5%, which is 95%. So if I wanted to look up this chi-squared value that cut off 5% on the left, I need to think about it as cutting off 95% on the right. Go back to the chi-squared table. We're still at 10 degrees of freedom, but 5% on the left means 95% on the right. So we're in the fourth column, going down to the 10th row, and we get a chi-squared value of 3.940. Let's go draw that. 3.940. So we can't take advantage of symmetry and opposite tails having opposite Z or T values because there are no opposites in this distribution. There are no negatives. Our chi-squared table uses right areas. So if we're looking up a left tail, we have to look up the area to the right of it, which is just 100% minus the area of the left tail. Let's try one more real quick just to give you an opportunity to practice this without me giving you the specifics and the answers. But let's say that we want to look up two different tails. Let's look up a 2.5% tail here. And let's look up a 10% tail over here. I know normally we would have the same percents in the tails, but this is just an exercise in looking up chi-squared values. And let's say that our degrees of freedom is 15. If you haven't done so already, go into Canvas and open up the chi-squared distribution, and I invite you to see if you can look up both of these chi-squared values. Just remember, chi-squared table needs to know the area to the right of something, even if you're given the area to the left of something. So pause the video and see if you can look up both of these chi-squared values. And if you're not pausing it, why aren't you? At this point, I'm going to assume that you either have done it or you haven't. I'm pretty sure one of those happens. Either you've done it or you have no plans of doing it. So let's look up the one on the right, which has 2.5% in the right tail and 15 degrees of freedom. Go to the chi-squared table. 15 degrees of freedom is this row down here. And 2.5% to the right would be the third column from the right. And if you found 27.488, then you found the correct chi-squared value. 27.488, I believe, is what I just said. Go back and look at it again. Yes. And while we're here, let's go ahead and look up the left chi-squared value that cuts off 10% in the left tail, if you will. Now, if you said 22.307, then you forgot that we need to know the area to the right, not the area to the left. If there is 10% to the left of the chi-squared value, that means there is 90% to the right. So we would look under the fifth column, the 90% column, in the 15th row, and our chi-squared value is 8.547. 8.5. It's not super difficult to look up chi-squared values. You just have to know what the chart is asking for, and then you just look up